go as high, that simply means that you're going to set up a loop for epsilon going from 0 to maybe 5 or 10 or whatever, okay? And when you get a converged result, you will take the norm and plot it, okay? The Newton method should converge. That should be your criterion. The error should be 10 to the minus 12, 10 to the minus 13 or whatever, okay? And that will stop happening once you cross a certain threshold. You're using Euler-Newton, you're taking a projection and giving an initial guess and say find the next solution. Suppose the limit point were here, that would fail. Newton method would fail to converge. And that's when you know that somewhere between where you started and where you wanted to get the solution, there is a limit point. Okay?
And there's a point they say like it's kind of say it's mere singular point. That means that it's approaching this turning point?
Yeah. The Jacobian becomes nearly singular.
Okay.
The condition for limit point is the Jacobian must be exactly singular. Right? There must be exactly one eigenvalue that is 0. So the determinant must be 0. So you cannot invert that Jacobian. Right?
From my graph, it's like a sudden. It's not. It's like it's about to turn, but it tell me something like that. Maybe it's going like this, and then it's coming at this point. It's kind of near singular, something like that.
Yeah, once you cross the limit point, that's when it will have difficulty, and it will say that it is near singular. Unless by sheer accident, as you are marching along, you end up very close to the singular point. Then also you will get that message. Yeah.
Also, for like a reverse path, should I try lambda very large, from very large to like 0 for the reverse path?
Yeah. For mu equal to 0, there is no solution beyond this.
Okay.
There is mathematical analysis of that shows that. The turning point that turns around and then just goes asymptotically to this. Okay. So only when you have mu greater than 0, you could find a situation where you come up this and then it jumps and it goes like that. Then you can start with this and say, okay, go back. When you're going back, it's not going to jump at the same position. It will go somewhere else and then jump. So you will have forward jump like this and a backward jump like that. And that will still not allow you to find the intermediate solution unless you give a good initial guess. Okay, so you could, for example, play with, take this solution and that solution, take the average of that and give that as an initial guess and see whether it goes back to the same one or somewhere in between. If it goes somewhere in between, then you can march forward and march backward from that to approach that point. Okay, so there are tricks like that that you can use to piece together. It's a puzzle, and I will show you some real problems today. These are what I call Mickey Mouse problems, and even that you are finding it pretty challenging. Okay, and how people use that in fluid mechanics, heat transfer, mass transfer problems to really solve more realistic flow problems. And the other thing I wanted you to check is only for one value of epsilon, I wanted you to solve the problem repeatedly for different number of grid points. And one of the things that we will show very soon is that this discretization has a truncation error of the order delta x squared. Okay, that is the numerical approximation that converts the differential equation, here it is, the differential equation into an algebraic equation. Okay, that's what we do here. By replacing the derivative, this is the method of finite differences. We're going to see the theory behind it in some greater detail later on. But this is not exactly equal, there is an error. And you can control the error by simply making your delta x between these 2 points smaller and smaller, so putting more and more grid points. And because you have the analytical solution, you would actually be able to compare the difference between the analytical solution and the numerical solution and plot it as the error, norm of the error. Again, you have a vector, so you need to take the norm of the difference between the solution coming from here and the solution coming from here. Okay, and plot that against n, and you'll find that it goes down as delta x squared. Okay, so actually you should plot it not against n but against delta x. Okay, and you will see whether you have a quadratic relationship or not.
Professor,
Yeah.
one question. In the finite difference method, I'm like programming. I'm dividing these equations in three structures. One is I'm only generating equations for the nodes, not for the boundary conditions. So when I equal 1,
Yeah.
I just say I minus 1 equals 0, and I just take it out from the equation just to solve that
Yeah.
problem that
Yeah.
of an error of that vector.
Right.
And the same for n. I just
Yeah.
take a 0. I take a. Is that
Yeah,
correct?
that's how you would impose the boundary condition on this problem.
Yeah.
When there are other boundary conditions, you will see how to handle that.
Okay.
But that's the
Yeah,
simplest
because
way in this case.
Because
Yeah.
there's no vectors with number 0, so I just take it away and.
Yeah. So your vector will be of length 1 to n.
Yeah, and I will have 1.
So if I say n is
plus
length-
2, because counting the boundary conditions, am I right?
Right, but the unknown vector length would be n.
Yeah.
And you can just throw away the known boundary conditions by imposing them in the equation. When you write this equation for I equal to 1, okay, you will have I minus 1, which will be 0.
Okay.
Just drop that from the first equation. And then you can put a loop for second to the nth equation, n minus 1th equation.
Yeah.
And when you have the nth equation, that will have n plus 1. Throw that one out. So you are going to write n equations.
Okay.
And then you can use that with fsolve. Yeah.
Does it drop to 0 because of the boundary condition, or is it dropping to 0 because of the way that we're implementing the finite difference?
The way that we are implementing the boundary condition in the finite difference method. Okay, this is the finite difference approximation
Right.
to the differential equations, and when you evaluate this, this is evaluated at every grid point. Okay, so you have grid point 1, you write that equation. So you will have u2 minus 2u1 plus u0. But u0 lies on the boundary, and the boundary condition tells me that it is 0.
That's what I was saying.
Yeah, that's what it is. Yeah. I think this kind of discussions are probably more useful because you have worked on it a little bit and you have some doubts and I can answer those and it resonates well with you. Any other questions? How are you guys doing at the PI on your current assignment? Any questions? I keep repeating this offer. If you need to meet with me online, let me know. Fix up a time, okay? If you're struggling with the assignment. This is a challenging assignment. And there are not going to be many assignments in this course, so I make them a little bit challenging. But at the same time, I would encourage all of you to start looking at the project. Okay, so this lecture is particularly going to be about how we take all these ideas and look at how people have applied it in the literature. So I'm going to take 2 or 3 papers from the literature and go through point out as you are reading the paper, you should be able to say, okay, this is what he's doing here to get this result. And that's the kind of thing I want you to do in your own project. Okay, the project should be driven by understanding what we have learned in this course and applying it for one specific example to produce one result. And then be aware of at least 10 other papers in your area so that you can write a decent literature review. And it's like a mini paper that you're going to write. Okay, that's what my expectation is. So don't delay it, don't postpone it, start working on it as soon as you can. Okay. So any other questions on the current assignment? Nope.
To Dr. Manal, for counsel. I'm using the form by coefficients. Can I use that to build my equation for
Yes.
Can I use the form by coefficients?
Which coefficient?
The PDE
Yes.
in one dimension.
You can use general PDE,
Yeah.
or there is a similar structure of equation like heat equation will have second order term and Poisson's equation will have second order term. So you could use any of those. You just want to make sure that the structure of this problem should resemble that, and you can make appropriate coefficients.
guess I lost all that. Now, let me ask you before I start today's lecture is going to be very high-flying. You're going to get the big picture, not the details. Okay, so the last 2 lectures or 3 lectures, including Reynolds, we learned the nuts and bolts of how to actually implement it, how to do it, so that you can do it in your current assignment. Okay, and towards the end of the last lecture that I gave, we were looking at the limit point implementation. Are you guys comfortable with that? Did you take a look at that lecture? That lecture actually had 99 views. I was wondering, are you viewing repeatedly or other people are viewing it? I don't know. But are there any questions on that? Can I leave it and move on to the high-flying part, or do you want me to spend some time on implementing? What I remember from the last lecture was that we looked at in detail how to write these 2 functions, CSTR f lim for the limit point and the CSTR j lim for the Jacobian of the limit point. And I have posted all these functions on Moodle, so you can take a look at it and work on that particular problem before you go to your current problem to make sure that you understand every line in the code. And that then makes it very easy for you to take that idea and implement it with your own problem. So it is essentially the Newton method, and I think I ran out of time, so I just showed you how to use it with fsolve. If you want, I can type this line and show how it works with Newton method, or if you want to see that function, I can show you the structure of the function. I think we discussed this briefly. Do you want to see the functions? Okay, so this is the function that we talked about. Okay, so this is remember the limit point, the turning point is calculated using an extended system, and this notion of an extended system should be becoming comfortable to you. So that you will see many more extended systems for many more types of singular points. Today I'm going to take you through that. But we have seen it twice so far. One is the arc length continuation, where reparameterize the problem and extend the system by adding 1 additional equation, which is a measure of the arc length. And then we are seeing it for the second time, where we impose a particular condition. That condition is an eigenvalue must be equal to 0 at that particular limit point. And when we did that, we ended up in this 2x2 problem, we ended up with 5 equations, the 2 original equations, and the 2 additional equations that come from the fact that the Jacobian times the this is the assignment, but I'll just use that as a whiteboard. So the first condition was that f(x) some parameter epsilon is equal to 0. So you could have any number of equations here. In our CSTR, we have 2 equations. In your example, you're going to have 19 equations. In some of the examples I'm going to show later on, coming from fluid mechanics, you'll have 20,000 equations. Okay? But essentially, these are a set of algebraic equations coming from some physical description of the problem. It could be a reactor, it could be a flow, it could be anything that you want. Now, what we want is, we know that a solution like this has a turning point. We want to find out where the turning point is. Exactly what is the location of the limit point. So we make epsilon as an unknown. So we're going to kind of tune epsilon, adjust it, and ask the question, for what value of epsilon, the Jacobian of this matrix, this function, has exactly 0 eigenvalue. So the eigenvalue problem in general is J phi equals lambda phi. J is the Jacobian of that function, and phi is the eigenvector. Now in this case, we have said that this is going to be equal to 0. I'm just recapping some of those. So we add an additional set of equations. J phi is equal to 0. Okay, so here we have n equations, and here also we have n equations. So the extended system becomes 2n plus 1. y plus 1 because this vector we do not want it to be 0. One way of satisfying this additional equation is phi is equal to 0. J is not equal to 0. But we don't want phi to be 0, we want J to be 0. What does it mean when you say the matrix has to be 0? It has to be singular, its determinant has to be 0. Okay? So we put the other condition, L of phi as equal to 1. L is a linear measure and norm, length of the vector. So this is the extended system that we are going to solve, 2n plus 1. And we have seen what it is specifically for that reactor problem with 2 equations. So we ended up with 5 equations, and those 5 equations are the ones that you see in this function. Okay? And there is no substitute for going and thinking about each line and make sure that you understand it. Okay? So the first equation is the first line in 17 is the first equation for the CSTR. 18 is the energy balance equation for CSTR. 19 is where we are calculating the Jacobian of the 2 by 2 system. Okay? And then 20 is where we are adding the third and the fourth equation of the extended system, which is nothing but the Jacobian multiplied by the null eigenvector. Eigenvector corresponding to 0 eigenvalue. Okay? And those are stored in locations 3 and 4. So we pass one single vector, capital X, which is going to contain 5 numbers. The first one is a guess for concentration A. The second one is a guess for temperature T. Third and fourth are the guesses for the 2 components of the null eigenvector, phi 1 and phi 2. And we really don't have a good guess, but we have good guess for the others. And the fifth one is your parameter. In this particular problem, that is Q. Okay, the flow rate is the controlling parameter. So we unpack those vectors from X into 14 and 15 and use them in the remaining. Okay, so line 20 is where we calculate J phi equal to 0. And then line 21 is the norm, which is phi 1 square plus phi 2 square minus 1 equal to 0. So all these equations are something equal to 0, but we are just calculating the function. We're going to make a guess for the 5 variables and calculate these 5 functions and send it to Newton. And it's Newton's job to drive all of that to 0 to converge. Okay, so the Jacobian of these 5 equations is what is programmed in this function. Okay, and I guess I didn't go through this in detail, but I'm not going to spend a lot of time also going through this in detail. It is essentially a copy of the Jacobian that we wrote for the 2 by 2 original equation, and you see those in line 17 to 20. Okay, those are the derivatives of the first function with respect to A, first function with respect to T, the second function with respect to A, the second function with respect to T, etc. You need to figure out in a piece of paper to make sure that you coded this right. And line 22 is the Jacobian for the middle part. So if you go back, you need to remember this. You can just keep reinventing this. That would be unfortunate. So if you take the Jacobian of this 5 by 5 system, you need to figure out where all the various elements go. Okay. And what we saw, the Jacobian of the 5 by 5 system will have a block structure. And the block structure will be, these will be the first n, this will be the next n, and this will be the 1. In terms of equations. In terms of variables, what would be this set of variables? The original state variable, x. Okay, and this one would be phi. I just want to see how many of you are paying attention, right? So that should be the second vector, second part of the vector capital X. And the last one would be the parameter epsilon or q, whatever that is. Okay. So in each block, then you will have to take the derivative of the first n equations with the first set of n variables. That would be your j. Okay. Then if you go to the second set of variables and take its derivative with respect to phi, we'll also get j. So j goes in here also. The same j goes in there, which you have already computed. Okay. And the first set of equation does not have any of phi. So when you take the first set of derivative with respect to phi, that will be 0. And the first set of equations with respect to epsilon, I have already calculated it in Euler-Newton continuation. Okay, so you will put that here, df d epsilon. So you need to figure that out, and we did that in great detail in the last lecture. But you need to understand that before you can understand the coding that goes with it. And here, the coding basically implements those things. Okay? So the first 2 by 2 matrix, and then the same 2 by 2 matrix is copied into the middle block of the block structure, 3, 4, and 3, 4. And then df dq is the derivative of the function with respect to q, which you have already written a code for. And we take that and put it into 1, 5, and 2, 5. Okay, those are what I showed you just now. This block, df dq is that block. Okay, and you need to figure out the new derivatives that goes in here, that is non-zero, that goes in here, that goes in there. Because these two sets of equations, the n equation and one, are new equations. Okay, and we need to take the derivative of those with respect to x as well as with respect to phi. But you will notice that the last equation does not have any x in it because just a no. Okay, so that block will be 0. And in MATLAB, anything that is 0, you don't have to initialize it to 0. It automatically does it for you. So you focus only on the non-zero elements. Okay, so that's, I guess I have done initialization to 0, but that's not required. Okay, so that basically takes the same input vector x with 5 elements and returns a 5 by 5 matrix. And the last part of putting all these two together is what is done in line 38. So maybe let me just run this. See. All right. So that's the first figure, Euler-Newton continuation. And that's the Arclan continuation, which is solved before, and it is executed. Hopefully the results will be there in the workspace, printed out. There. Okay. So the question that I was asking towards the last lecture is, how do I know that the solution is the correct solution for the limit point? And do you remember what the discussion was? How would you verify that? This is a solution. This set of vector x satisfies the function CSTR at the limit. So if I pass x to that, I should get 10 to the minus 12. That is the tolerance I asked for. So those 5 values satisfy those 5 functions that I have written, possibly with errors, right? So I'm solving the wrong set of equations, and I get that function satisfying those equations. So that may not be the true limit point, because if I had made any mistake in the function, 5 of those functions, I would be getting the wrong answer to that. So how do I verify that this solution, in fact, is the solution for the limit point? What is the condition that we wanted to impose? That the Jacobian must be singular. Determinant must be 0, right? Yeah. So I could make a call to the Jacobian CSTRJ, passing the first 2 values, right? So CSTRJ x. So what do I expect this function to return?
Jacobian.
I expect it to return a 2 by 2 matrix, which will be the Jacobian, using the current values of x1 and x2, that is a and t, at the solution. So the solution is stored in x, capital X, right? And you have the capital X vector in your workspace, and you can double click on it and see what the values are. So I'm taking only value 2 and 3. Okay? Sorry, 1 and 2. I should take 1 and 2. 1 is for A and 2 is for temperature. 3 is for what? Phi 1, and 4 is for phi 2, and 5 is the actual limit point for Q. Okay? So if I enter this, I should get, let me store this in small j. I need to specify the parameter through, thank you. So I need to specify the same value of the parameter that was stored in that vector. So what would I enter here? Let me ask you that.
x5.
x5. Okay, now I can say what is the determinant of j? 2 to the minus 13. Okay, so that is the precision I imposed, right? So that is telling you that the values that you have, in fact, give you a singular matrix at that point. Okay, so any questions on that? Silent. How are you guys doing? All right, if there are no questions, let me just move on to, pardon me, any questions? Oh, Rashid is typing something. Why did I put x5? Okay, good question. The reason is I forgot that the CSTR j function, which I'm displaying now, requires two input arguments. One is the vector x, which contains a and t, and the other one is the parameter q. Because these functions and the Jacobian depend on q, what value of q we have. Okay? So x5 is the place where I have stored the solved value for q, the true limit point for this particular problem. And that's why I put x5 in that location. So this must accept the value for q at the limit point, which was solved and stored in this array here, in the fifth position, 9.701. This is actually accurate to about 12 decimal places because our tolerance is like this, but it's displaying only the first 4 decimal places. Okay? And so the first two contain the converged solution for a and t, and the CSTR function, j function, requires us to specify also the parameter in this here position lambda. Okay, that is the same as q. So I need to put in the value. Is that clear? Okay, good. So if there are no other questions, what I want to do today is take you through very quickly some of the what we call canonical forms of various branching structures that you will find for nonlinear problems. And for each one of them, there is an extended system that has been developed. This happened very vigorously in the 1980s by applied mathematicians. They were just loving to go after finding each type of singular point, what is the condition that must be satisfied, and develop the condition. The problem in terms of applying this to real situations was the size of the extended system just goes up tremendously. If you take, for example, the limit point, I have 40,000 equations. You're solving it in console for a two-dimensional problem, flow past a cylinder. Okay? Then the extended system would be 40,000 times 2 plus 1, 80,001. Right? So it simply doubles. That is for a simple limit point. If you go for what is called a double limit point, it will just go again twice up. If you have a Hopf Bifurcation point, it will go up. But the theory behind each one of these singular points has been well understood. And that's what I'm going to take you through. So this part of the course is survey, to expose what is possible, the art of possible. Okay. So in an exam, you should be able to just converse, but not develop any of the ideas. Okay, in the oral exam. But what you have done in your assignment, variations on that, you should be actually able to develop on the board how you will develop the extended system for a particular case. You should really understand that well. If you understand it once, then it's just additional work for variations. These are all variations on the basic theme. Okay, so what we have seen so far is the so-called fold bifurcation, and a canonical, a sample example, classic problem of that is dx dt equals a minus x squared. That's a dynamical equation. By dynamical equation, we mean that the state variable x changes with time. Okay, t is the time. And the function on the right-hand side has certain parameters. In this case, a is the parameter. And there is certain initial condition. Okay? So what is the dynamical response of this as you integrate? And we're going to see algorithms for integrating ODEs. But the steady state behavior and the dynamical behavior are intimately coupled. And what this shows us is, I'm focusing only on the steady state by setting dx dt equal to 0, which means f of x equal to 0. I need to find all those values of x that satisfy that function equal to 0, and then see how those solutions change as I change a parameter in the problem. In this case, it's 8. Okay? So a bifurcation diagram is one where you plot the parameter a, or q, or lambda, or epsilon, whatever it is, the parameter appearing in the problem, against a state variable. In this case, the state is x. Okay? So we need to find out all the state variables under steady state condition and plot them. So in this particular, these are trivial examples, but illustrates the concept very clearly. Okay? So in the trivial example, when is this equal to 0? X square equals a, x equals plus minus square root of a, the steady state. Right? So there are two steady states, one corresponding to plus, the other one corresponding to minus. So that is your steady state solution. And the steady state solution continuously depends on the parameter a. What happens to the solution when a is negative? It's imaginary, right? So we don't worry about the imaginary roots, we worry about the real solutions. So the real solution exists only for positive values of a. And there is a positive upper branch and a lower branch. And if you start anywhere with your initial condition for this problem, that is, go back to the dynamical situation and say, I'm going to put some initial value for x and see which one of these two solutions it will go to. Okay? So if you start, for example, if your a is somewhere here, and you start with this as your initial condition, it's closer to that solution, so it will go. That would be your guess, right? So if I start here, what would you think? If I have mapped out the steady state solution structure, so I know that there are two solutions. Now, the dynamical solution means that I'm going to plot x against t starting with some initial condition. So if my initial condition is somewhere here, you would expect a trajectory maybe like this. Once the trajectory reaches a constant value, dx dt equal to 0, that is your steady state, right? So that's one way of getting to the steady state. My question is, in this diagram, if I start from somewhere here as my initial guess, initial condition, I should say initial guess, initial condition to the dynamical problem, as I plot x versus t that satisfies this differential equation, okay, the path on the state space, remember, this is why I talked about all these ideas of state space versus time series. This is a time series solution. This is a state space solution representation. So in the state space, we are plotting only the state, but time is parameterized. Okay? So this is time equal to 0, and you take every point from this and plot it, and the trajectory will be like this. So these arrows show how they are attracted. So if I start with some initial condition here, it will be attracted along this to that steady state, right? My question is, if I start somewhere here, what would happen? Will it go to the top or the bottom? How many of you say bottom? How many of you say top? Why?
Because I'm looking at the arrows.
Very good. Did you guys follow the answer? He said he was looking at the arrows, and the arrows tell you something. Now let's understand that. Why does the arrow tell you that even if you start from here, it's going to go to this, and if you start from here, it's going to go away from that? So what does that say about the bottom solution corresponding to minus a, minus square root of a? It is unstable. This is why I said the steady state and the dynamics are kind of interrelated. Okay? If that steady state that satisfies this differential equation, but that algebraic equation, but is unstable, then no matter how close you start to it, it's just going to go away from that. Okay? That will be the state space trajectory that is plotted in this. Now, how do I determine that? I determine that by simply going back to this and linearizing this model and calculating the eigenvalue of the linear model and decide whether the eigenvalue is, real part of the eigenvalue is positive or negative. Okay? This is for those who are control people, you have done this all the time. And all of you have taken undergraduate control course, right? So it should not be very new to you. But let's just go through the process of linearization of that equation to answer that question. Okay, whether it's going to be stable or unstable depends on whether the eigenvalue is positive or negative at the steady state, at these steady states. Okay, so this is my steady state solution. Okay, so if I'm given a dynamical equation, something like dx dt equals f of x, just a single equation. Okay, so what I'm going to do is I'm going to write the dynamical solution x as a function of t as equal to the steady state xs plus the perturbation around the steady state, and I'm going to say that the perturbation is small, and that is the idea behind linearization. Okay, so the linearization dictates that this is a small number. Then I take this decomposition of x into xs plus xt and plug it into the original equation wherever I have x, because x is being decomposed into the steady state plus a small perturbation. Steady state values are constant numbers, right? They don't change with time. So when I take the derivative of dxs dt, this will drop out because xs is the steady state. Okay, but so on the left hand side I just get dx prime dt. On the right hand side I will have a Taylor series expansion of this. Okay, that is f at xs plus df dx at xs at the steady state multiplied by the perturbation x prime plus the higher order terms. Because I'm linearizing it, I'm saying the x prime square, x prime cube terms are going to be smaller. So this is the dominant term. So I'm going to truncate my series, Taylor series with that. Okay, and what about f of xs? That will be 0 because that's how I find xs, the steady state, right? So this will automatically be equal to 0. So the equation reduces to this for the perturbed variable. So all I'm looking now is whether the perturbation is going to go away to 0 or is it going to grow. If the solution to this is an exponential with a positive part, it will grow. That means that solution will be unstable. Okay, but so that is why the dynamics of the nonlinear problem is locally determined by the Jacobian at the steady state. Okay, so this is applicable whether you have one equation or 100,000 equations. But if you have 100,000 equations, the computational challenge becomes very difficult because you need to calculate 100,000 eigenvalues before you know one of them is positive or not. Okay, so we need to develop clever methods of how we can track only the subset of eigenvalues that are just about to cross. If you plot, for example, the real part versus the imaginary part, real lambda, the eigenvalue versus the imaginary part of the eigenvalue. For 100,000, you'll have eigenvalues everywhere on the left part. There will be one or two that are trying to sneak to the right half, and you need to look at them. And when a parameter changes, that's the key. When a parameter changes, all these eigenvalues will change, and we need to track how they are changing. Okay? So all the ideas that we have seen already for linear systems, how to solve the linear system, etc. Okay? So we are now applying it to gradually more complicated set of problems. So any questions on that? So what you should understand what is linearization and why that eigenvalues of the Jacobian give you information about the stability. Okay, because the solution for x prime is given by something like this, e to the power lambda t. Lambda is the eigenvalue. So take that, plug it into this equation, and you will get an eigenvalue problem. And I think we have done that before, right? The eigenvalue problem in this particular case is going to be trivial, but in general, if you take this and plug it in here, you will get j x hat equals lambda x hat. X hat are the eigenvectors, and j is the Jacobian of that particular function. Okay. So we need to solve the eigenvalue problem, but for a 1-by-1 system, lambda is nothing but df dx at xs. So in this particular problem, lambda is equal to what is the derivative of this function? Where is that function? Let me just pull it back. It is simply a minus x squared. So what is the derivative? What is the Jacobian of that? Minus 2x. Evaluated at the steady state. Minus 2xs. Right? X subscript s. And that's what we are saying, minus 2xs. But we know what the steady states are. The steady states are plus a. So when it is plus a, when I substitute for xs as equal to plus a, what can you say about the eigenvalue? It is always negative because I have a minus sign before. So that is the solution that is stable. Okay. When xs is equal to minus a, that is the other solution, the lower part, the minus and minus sign will flip, and I will get a positive eigenvalue. And that is why in this particular case, the lower branch is unstable, and the upper branch is stable, and that is typically indicated by the solid line versus dotted line. Okay, and that is the reason why even if you start from a solution close to that lower branch, you will always go to the other one because that's a stable solution. That will be an attractor. Okay, as it approaches this, it will be a repeller, and we saw this in state space with two equations, various types of possible responses. You could have in a 2 by 2 problem, you could have one positive and one negative. Then you will get something called the saddle node. It is attracted through the stable manifold, submanifold, and then repelled through the unstable one. So you should review those figures that we saw in solving a system of linear ordinary differential equations. Any questions? Yeah.
So we cannot find this unstable solution irrespective, like whatever guess we do with this set of equations.
No, that's a good question. The question was for people at PI, does that mean that we cannot compute the unstable solutions? And the answer is no, you can compute them. Okay, and that's a very good question because if you try to compute them using an integrator that integrates the dynamical system, you will not be able to get there because those are unstable systems, and the dynamical equations captures the true dynamics. That means you are integrating this equation. Sorry. Okay, so if you are integrating this equation, I'm talking about the dynamical equation there. Okay, then you will not be able, no matter what even if you put your initial condition right on the steady state, because there are round off errors, it will stay there for a while, but the error will accumulate and it will blow away. But you can get those solutions and you can know about those solutions. How can you do that? Newton method will give you, because Newton method is guaranteed to converge, no matter whether the solution is stable or unstable. It's blind to the stability of the dynamical stability of the real system. So this is some concept that you should get introduced to, that is numerical stability versus the physical stability of the problem. So this problem exhibits a physical instability in the lower part. But if you apply the Newton method, and this problem of course you won't because you can write the solution analytically, but if you have a problem like in the CSTR, you are able to compute. There are solutions that are unstable in the CSTR problem. Okay, when you turn, the middle branch is unstable. And I think I asked you to calculate the eigenvalues of those. You will find that the middle branch is unstable, but the Newton method will converge without any problem, converge quadratically. Okay, so the convergence of the Newton method is independent of that dynamical response. But if you use an ODE integrator, then, and if you do an experiment, you'll also not be able to get it. Okay, so this was a kind of a great advance by Benjamin. I still love that particular paper. I think it came out in 83 or something like that, early 80s in the Journal of Fluid Mechanics, on the bifurcation theory in fluid mechanics. And he lays out the theory so beautifully, drawing results, very advanced results from algebraic topology, etc. And he has something called the index theory, which assigns a particular index, +1 to stable and -1 to unstable. And when you have a complicated structure of many branches, the index should not change. So you can use that to detect. If the index changes, that means there is some other branch that we don't know about. And it's a very good tool for experimentalists and computational guys who are doing dynamic simulation, not using the method of algorithms that we have seen so far. Algorithms that we have seen so far are excellent for piecing together the jigsaw puzzle completely. And I'll show you how complicated the puzzle can be in today in some of the other papers. Okay, but that's a good observation. A stable solution or an unstable solution, you should be able to still compute using the Newton method or the Newton continuation, etc. Any other questions? Now we're going to repeat the same thing for different types of bifurcations. So pitchfork is something that we have already seen. The pitchfork typically has a behavior like this: a state x versus a parameter epsilon, and you might have a behavior like this. That is what we will call a pitchfork bifurcation. So there is one branch that goes continuous, but then there is a kind of a limit point intersecting across that. And we saw an example, a physical example of a bending rod that Benjamin proposed. A mathematical representation of that is given by this dynamical equation, where you have two parameters, A and B. The state is x, single equation still. So this is called a canonical equation because whenever you have this kind of a bifurcation picture, okay, around that, you'll find that the algebraic behavior is represented by this kind of thing. Even though the equation may look very complicated, you can develop a model that fits this particular type of behavior with two parameters. So the first thing that you do is look for the steady state. So set f of x equal to 0 and solve for that. So you can factorize this as xs multiplied by a minus b xs squared equal to 0. So how many roots are there? It's a cubic. You must have 3 roots. Okay. Obviously you will have 3 roots. 1, 2, 3. Okay. But for certain values of the parameters. So a and b are two parameters. We are letting a to be anything, but b must be greater than 0. Now b is less than 0, you will find the inverse image of that, which would be called a subcritical pitchfork. This is called a supercritical pitchfork. In the sense, it occurs as a continues to increase. Okay. A subcritical one will look something like this. Okay. So we can solve for these. Okay, so xs equal to 0 is one solution. Okay, and xs equal to plus minus square root of a over b, which comes from the second part of the equation, setting that equal to 0, is the second solution. So there are 3 solutions. Okay, and linearize that. When you linearize that, you get your Jacobian, and you can evaluate the Jacobian at the steady state, xs equal to 0 and xs equal to plus minus square root of a over b. So for each one of those steady state solutions, you can determine the stability from this particular Jacobian. Okay. So xs equal to 0 doesn't have a in it, it doesn't have b in it, right? So that solution exists. Now let's take that this is for some value of b greater than 0. This picture. Okay. So a is the distinguished parameter that I'm fixing b to be constant and then changing a. Okay. So what happens when xs equal to 0? There is a solution that goes all along. Xs equal to 0 is a solution for all values of a, right? But xs is equal to plus or minus a over b is a solution only for b greater than 0. Okay, and that is the plus, the upper part, and the minus, the lower part. San Diego may tell what the stability of each one is because he has picked up already the signature, right? The signature is, if you start from here, it is attracted to this. So that's a stable solution. Okay. If you go to the right, you start from here, it is attracted to that. Start from here, it's attracted to that. That means even if you start very close to this 0 steady state solution, it's not going to stay there. The dynamical equations will cause it to go to the other one. Similarly, this one, the lower branch is sustainable. So the upper branch and lower branch both are stable. And I'm going to show you a physical example from fluid mechanics, hopefully today, that has this kind of a behavior and a much more complicated behavior as well, but built around this idea. Okay, so you can very easily understand that. So when x is equal to 0, j is equal to a, and when a is negative, it's stable. This part is stable. When a is positive, it's a positive real root, right? The solution depends on e to the power at. So this will all be unstable. That's why it's shown by dotted line. Okay. The dotted line that you see. That stands for unstable solution. This is a stable solution. This is a stable solution. That's a stable solution. Okay, and you can confirm that the upper and lower are stable solutions by substituting for XS in here, A over B. So what do you get? So J you would get as equal to A minus 3B times XS squared, so which is A over B. And B and B will cancel out, it will give you minus 2. And A is positive, right? And it is minus 2A, so those are going to be stable solutions. Any questions on that? We are still not flying, we're just taking off. Okay, so the next one is called the Hopf bifurcation point. And for this one, you really need at least 2 equations. Okay, the previous canonical examples was just simple single equation you could explain. Excuse me. So we have 2 dynamical equations, the 2 state variables on X and Y, and there is 1 parameter A. Okay, it is a nonlinear equation. Obviously, you need nonlinearity. For linear systems, we know we can actually analytically write down the solution. Okay, but you need the nonlinear equation. So, what is the steady state behavior? Set each one equal to 0. Okay, and you get X is equal to 0, Y is equal to 0. By inspection, you can look at it. If you put X equal to 0, Y equal to 0, this equation is satisfied. Doesn't mean there's only one solution. There could be other solutions to that particular set of equations. Okay, but we know at least this one exists. That is always a problem with nonlinear problems. You don't know, there is no theory till today a priori how many solutions there are for a given equation. If you ask a question, how many solutions there are, the answer is we don't know. If it is a polynomial type of nonlinearity, you know. The degree of the polynomial is 5, you will have five roots. Okay, but anything other than that, you cannot tell beforehand. So we need to evaluate the Jacobian at the steady state. The steady state is this. Okay, the Jacobian of a 2 by 2 system, and then look at how that Jacobian behaves. Okay, so the Jacobian is nothing but df, the first function with respect to x, first function with respect to y. Take those derivatives and put xs ys equal to 0, and you will get the Jacobian at the steady state to be this. Okay, and the linearized example then looks something like this. And the eigenvalue problem is j minus lambda I equal to 0. Now j is a 2 by 2 matrix, so there are 2 eigenvalues. You can actually at this stage pass this to Eig function in MATLAB and get what the eigenvalues are as you continuously change A. And what happens is, analytically it can be solved. That's the beauty of a canonical example. You build it so simple, but it still has all the information that we need to understand. So the eigenvalues for this one are given by A plus or minus square root of I. Okay. So what happens to the solution when A is less than 0? We want the real part to be negative. So when A is negative, it's stable, right? What happens if A is positive? It's unstable. Which is unstable? Which is unstable? The solution xs ys equal to 0 is unstable. Okay, so we need to represent that solution in the state space, and that's what this is the x-axis, and there is a y-axis. This is the 2 states. Okay, so the solution is a point in the state space. So if A is less than 0, we have a stable state. So if I start from some initial condition, the trajectory will be attracted to this in a cyclical fashion. Why to a cyclical fashion? Because I have a plus or minus I. The I is going to give me sine and cosine, right? And so no matter where I start, if I start from here, I might go somewhere like this. If I start from here, I might go somewhere like this, but it's an attractor for A less than 0. But what happens for A greater than 0? That solution is a repeller, right? So even if I start very close to that solution, what I will find is that it will just go away from there. The question is, where does it go? What happens? Sometimes it may go to a different steady state that is stable. But in this particular case, it goes to something called a limit cycle, which is a closed loop, a circle. How nicely I can draw the circle. Okay, but I think you see the circle there better than what I can draw. I'll just highlight it. Okay, that is the closed loop. So what it tells you is that if you start from somewhere outside, it is attracted to that circle. It comes and merges on the circle and then repeats. Forever goes on the circle. Okay, if you start anywhere inside, it is the inside solution is repelled, but it is also attracted to the same limit circle. Okay, so limit circle need not be a closed circle. It is a periodic solution. So the trajectory could be something like complicated structure. Okay, but it is a closed structure. So if you start from somewhere else, it will just be attracted to that. Wherever you start, it will be attracted to that, and it will just forever go on in that. So there is no steady state in this situation. It is a truly dynamical response. A lot of natural systems behave like that. Okay, you just increase exciting the forcing function, like increasing the Reynolds number. In flow problems, you will find it spontaneously switches to these kinds of modes, where the solution from being steady, it becomes time dependent. Did you have a question?
Kind of. The nature of the closed loop, since, I mean, you can't say it's steady because it's not one value, but it's kind of like it'll stay within certain bounds.
Right.
Are those bounds always, I don't know the right words, like reasonable, or like are they always somewhat close together? Is it always like if it's, let's say you're plotting temperature or something, will it always stay within a certain range?
Okay.
Or could it go
Now you are putting that
degrees, like negative 20, you know?
Yeah, that is a very valid question. You do have temperature runaway conditions, and the reactors exhibit this kind of a cyclical looping under certain conditions, and you want to know where they are and stay away from those regions, or better still, come up with control strategies that will kill this dynamics. Okay, so there are a lot of papers in those along those ideas. If I have a reaction system that shows oscillations, wild oscillations, what can I do? Can I introduce a feedback control system that will replace these eigenvalues? What is control system about? Placing the eigenvalues in the left half plane so that you have a stable operation, right? And that's all control system is, right? And a lot of people have borrowed those ideas to kill this kind of a complex dynamical behavior. But your question of whether they should be small or large, I think if you look at the dynamical equations of planetary motions, they are not small, they are large, but it depends on the scale in which you are looking at, right? So 10 degrees may be too large in certain applications, 100 degrees may be fine in other applications. The basic point is that you don't have a steady state. This is where the concept of Lyapunov stability will come in more attractive, because we are not saying that it should go to a particular point in state space. If it remains confined in a certain region, you'll still call that as a stable state, and it allows that kind of a generality. And so you'll call these as equilibrium solutions. Okay, they repeat themselves, but they are not. The dx dt is not equal to 0 at any point. Okay. Now the question is, the linear stability doesn't tell us that such a limit cycle exists. The linear stability just tells us that the xs ys equal to 0 solution is unstable at that steady state, right? So, but the other signature that we see here, which is the key for extending the system for detecting where a Hopf bifurcation point occurs, is this occurs when A is equal to 0, right? This change of stability from a steady state to a limit cycle occurs when A equal to 0. And that means I need to have a pair of purely imaginary eigenvalues crossing that axis. That is an indicator for a Hopf bifurcation. What do I mean by that? If I plot the real part of the eigenvalue as a function of the parameter A and the imaginary part of the eigenvalue as a function of the parameter A. There is a parameter in the problem. As I change the parameter, the eigenvalues change all over. So in this particular case, it changes in a fairly simple way. It is A plus or minus I. Okay, so for some values of A, it may be something like this, right? But as A goes to 0, the real parts goes to 0, they are here. Real part of A is 0, right? So they are crossing. What am I doing to make the cross? I'm changing A, right? So the eigenvalues change as A changes, and when A is equal to 0, they are exactly on the y-axis. A pair of purely imaginary eigenvalues. There is no real part. It is that condition that we will impose as an extended system to locate where that Hopf bifurcation point is in real problems. In this made-up problem, we know it is at A equal to 0, right? In all these made-up problems, we understand the core of the idea, but we know where the roots are. We have placed the singular points at a certain position. In this case, we have placed it at A equal to 0. But learning this concept that I need to impose occurrence of a purely imaginary eigenvalue will allow me to then say, okay, where is the value of A that makes that eigenvalue purely imaginary? Okay, that's an extended system that we will see in a paper and learn how to interpret those things, because that's one of the things that I found as a graduate student to get over. I needed the help of a mathematician to kind of guide me through. Okay. Any questions on this concept of what a Hopf bifurcation is? A Hopf bifurcation point is a point in the parameter space where the steady state loses stability to a periodic state. Okay, and in the simple case, you can see when A is equal to 0, lambda equals plus minus I, the solution should be sine I and cosine I. That's why for this ideal problem, the solution will actually be a circle. Okay, but this problem allows us to actually construct the solution analytically for the full dynamical equation. You don't have to use the ODE 4-5 integrator. You can solve that particular problem if you make this coordinate transformation: x equals r cos theta, y equals r sin theta, or x plus iy equals r e to the power I theta. Okay. Remember, the two equations are, you need to make the coordinate transformation on these two equations. Wherever you have x, put r cos theta. Wherever you have y, put r sin theta in these two equations. And then simplify it. And magically, it will simplify to the following form after one page of algebra. Equation will become this. Take a moment to study that and tell me what you observe. These are the same equations in the new variables, new coordinate systems. XY coordinate system is a Cartesian frame, and this one is a cylindrical frame, r theta, right? What do you notice? In the original equation, we had two equations: dx dt equals something, dy dt equals something. But the first equation, dx dt, depended on both x and y, and so did the second equation. So it was completely coupled. What do you see here? It's completely decoupled. Okay. So, and this equation is easy to integrate. You can separate and integrate. Just a quadrature evaluation. Just take this to the left-hand side, take this to the left-hand side, and separate and integrate. And you will get this as the solution. And that is trivial to integrate. D theta dt is 1, theta is t. Right? And there is an initial condition. So the initial condition is x0 or 0. So what we are saying is, instead of treating these, it's the same equation in terms of x and y, you can treat them as r and theta. The same point in the state space can be represented either in the xy frame or the r theta frame. We have the equations for both, and in the second framework, we are able to actually integrate and get the solution. Now look at the behavior of the solution. This is a full nonlinear equation. It's not linearized, right? It is still nonlinear. You can see the cubic nonlinearity there. So how does the solution behave for a less than 0? You know that it is stable, but look at the term. This term doesn't depend on a at all, the theta component of it. What about the r component? As a is negative, you'll get e to the power a positive number. As t goes to infinity, what happens? What shrinks?
R.
The r shrinks, right? The denominator goes to infinity, so the radius shrinks. And that's why if you take a plane where a is for negative, and on that plane, so a is the parameter here, okay? And this is x, y, or r theta on that plane. So if you start anywhere, you have an initial radius r0, and the trajectory is going to just shrink to r equal to 0. And that's why from this one you can determine that it is going to be stable. Okay. For A positive, what happens? As t goes to infinity, this term will think carefully. Think carefully. Question is, what happens when A is greater than 0 in this term? So that term will become 0. If that term becomes 0, this entire term becomes 0. This entire term becomes 0 because the exponential term drives it to 0. Then you have A r0 square over r0 square, which becomes A as a continuous function of time. So for every time, all instants of time, radius is A. Okay, that means if I am in a plane here, on the right hand side, I take a plane. Even if I start very close to it, there would be a transient part, but then it will go on to the circle with a certain radius A, and it will stay on that state as a closed circle. But what happens to the amplitude of that circle as A becomes large? R is equal to A, right? So the radius of that circular trajectory will become larger, and that's why we represent the Hopf bifurcation like this. This is a steady state part that is stable. This is the steady state part that remains as a solution, but it is unstable. But the trajectory beyond that is a closed circle with increasing amplitude in this particular case. Okay, as A increases, the amplitude of the radius increases simply as A. So you can see the problem has been nicely fixed so that interpretation is easy to get. Okay, and so in these curves, t is the parameter. So when I start t equal to 0, t equal to 1, 2, 3, 4, etc., will continue to change. So t is changing means theta is changing. That's why it gives you the circular orbit. R is constant, but theta is changing continuously, and that gives you the circle. Okay, so that is the characteristic feature of a Hopf bifurcation point, where you have a steady state losing stability to a dynamical state, where you have a periodic solution that emerges. Now it's possible that you will have another Hopf bifurcation from somewhere from this Hopf bifurcation, and the period may be doubling. And in the undergraduate course that I'm teaching now, I gave an assignment from a CSTR reactor problem with 3 ordinary differential equations. Of course, we don't talk about any of these ideas. All they're learning is how to integrate ODEs. But integrate this ODE for a set of 12 parameters. And I got an email last night saying, I'm puzzled, what is happening here? The same problem, the same equation, you integrate it for 12 different parameters. Maybe take a look at that. And you will see that the first parameter value, it's a steady state. For the last parameter value, it's a steady state. Parameter is continuously increasing. But in between, it goes through 1 cycle, 2 cycles, 3 cycles, through a chaotic regime, back to periodic state, and back to a steady state. So it's really a very fascinating example. The book by Scott, it's called Chemical Chaos, is full of such dynamical systems drawn from chemical reactions. Okay? So it's a very active area in terms of the dynamical responses of complex reaction systems. But you'll find this in anywhere. In fluid mechanics, I'm going to show you a few today. Any questions? How are you guys doing? Okay, that's Hopf bifurcation point. This is what I was saying, that the eigenvalues will cross that imaginary axis at the Hopf bifurcation point. Lorenz Attractor. How many of you have heard of Lorenz Attractor? A few, right? This was a work that was done in 1963 by a professor at MIT, an atmospheric scientist. And so he published it in Journal of Atmospheric Science. The origin of this is, the equation is Navier-Stokes equation. Okay, he was trying to model, understand the dynamics of convective motion in the atmosphere. And it is really surprising that you could represent something so complicated by 3 equations. In fact, in reality, you cannot. Okay, but 3 3 equations can capture the entire complexity that you will find in the full-blown weather modeling system or the Navier-Stokes equation. Since then, a whole book has been devoted to the Lorenz equation, Bifurcations, Chaos, Strange Attractors, by Colin Sparrow. Okay, so those who are curious, interested, you can look at the original paper as well as the book on Lorenz equation. It's essentially 3 ordinary differential equations, as I said, derived from the Navier-Stokes, and I will show you another example where you will get some idea of how this derivation takes place, how this reduced order models are developed from the partial differential equation, just to get an idea. Okay, you really need to spend a lot of time on each one of these problems if you want to understand. So the purpose of this course is to kind of expose you to all the exciting things that are out there. Maybe 1 or 2 will I guess tickle your imagination, and you can then spend time learning more about it. Here, x, y, z are the states. There are 3 state equations, and there are a number of parameters. Parameters are PR, Prandtl number, R, and B. Okay, so you'll see that PR is one parameter, R is another parameter, B is another parameter. It's a coupled nonlinear ordinary differential equation. Okay, and there are several steady states. The steady state analysis itself is very fascinating. But for our purpose, there are a lot of parameters. So the problem is very rich in terms of the dynamical behavior that it can exhibit. But for R greater than 1, okay, you can solve these equations and get the steady state as xs, ys equals plus or minus b r minus 1 and z equals r minus 1. That's one solution that will satisfy that equation. Okay, mathematicians have gotten into this and have done a lot of analysis on this particular problem. But originally what he did, he meaning Lorenz, solved this problem for this particular set of values. PR is 10, B is 8/3, and R equals 28. I don't know whether you guys know the historical story of what really happened with him. This was in the 60s, and he had a desktop computer that was just with a teletype printer. So you'll set the problem overnight to integrate these 3 ODEs. Nowadays you can get it before you click a finger. And he would set this overnight and go back and come back and see how far it has integrated the next morning. And one morning he came and he saw certain numbers for x, y, and z at a certain time. He said, well, I would like to see a little bit more of integration. So he took those numbers and reinitialized it, re-entered as the initial condition and started the integration. But when he did that, he truncated some of the numbers from 7 digits to 4 digits or whatever. And one day goes on and he gets a completely different picture, right? And for us, we will say, well, something is wrong with the program, something, so we will just dismiss that. He did not. And that's what led to this deterministic, I like this title, deterministic non-periodic flow. What does deterministic mean? It means that if you know the current state of a particular system that you are studying, if you have a deterministic model like this, you know its future forever. If you know the current condition, it is determined. The future is determined by the current condition. As opposed to stochastic modeling, where you introduce random variables and probabilities, right? Here, if you know the current state, you should be able to predict. But this was the first paper that pointed out maybe you cannot predict, okay, even if you know the model very accurately. And what he obtained was the following. This is a time series, just plotting x versus t. If you plot y versus t or z versus t, it will look exactly like this. And if you see a signature like this, what do you think immediately? Some sort of a random variable, right? Some sort of a random variation is occurring. So the question is, can I go back and put the same initial condition here and expect to reproduce the same graph? That's what determinism means, right? And if you don't carry the significant digits in your calculation, which is what he did when he restarted it, he rounded off the errors. And you'll find that the long-term trajectory may have signatures like this, but doesn't overlay on this one. It looks completely different. Okay? And when in this view, it looks like there's some element of randomness in the model entering from somewhere. And later on, people understood as causes for this, the sensitive dependence on the initial condition is one of the key features when you're seeing behavior like this. But when you plot this in the state space, the picture looks beautiful like this. What is this? It's the same solution, time series solution, but plotted in the XYZ space, the state space. Okay? So T is parametrized. So if I started, for example, from some initial condition like this, XYZ, for T equal to 0, I might have an initial transient like this. But then it goes there, and then forever, we will just do this. We have seen closed loops, which are called limit cycles, right? But this is not a limit cycle. It never closes on itself. And it is, if you keep integrating it, it will continuously fill the space. So this is called a space filling curve in some sense, right? So one of the theorem in ordinary differential equation in fact says that a trajectory of a solution cannot intersect. Okay, there is as long as the function dx dt equals f of x, right? This is the integration equation that we are integrating. Okay, so if f is continuous function, then there is a theory that says that the solution is unique. Now, we need to be careful. When I say the solution is unique, I'm talking about the solution to this dynamical problem. That is, I'm talking about in the time series x versus t, if I start with some initial condition, there is only one curve that will satisfy that equation. For each initial condition, there will be one unique curve that will satisfy that equation. But the steady state is not. If I set this equal to 0 and look at the steady state, there could be many, many different steady states. Okay? And different initial condition could attract to a different steady state. This could be a second steady state. If we start from somewhere, I may never have a steady state. I may have an oscillating state. But that curve will still be unique as long as this function is continuous. Why is that? It's very easy to understand conceptually, but there is a rigorous mathematical proof. The easy understanding of that is, in the state space, if I have a trajectory crossing, that is, this is at t equal to 0, and it starts like this and goes around and comes back and crosses it. It can never cross. Why can't it cross? Because if I give the crossing point as my initial condition, then which direction will it go? Right? Once it went this way, and then when it comes back, it says it's going this way. So if it is a true intersection, then I have an ambiguity. There is no uniqueness to it. But the theorem dictates that there must be a unique solution. Okay? So the trajectories can never cross. And that means if you have only two state variables, what is the only possible solution? Either there is a steady state or there is a limit cycle. Okay? Because the limit cycle is a closed loop, it never crosses itself. Okay? But if you have three equations, and this is an important difference, when you're going from two equations to three equations, you get a much richer response that is possible, because this trajectory will never cross, but it will still have enough degree of freedom for it to continuously scan the space and fill the space. And that is what is called a strange attractor or chaotic response. Okay? And at one time, turbulence in fluid mechanics was thought to be caused by such changes. And in fact, this equation comes from fluid mechanical equations, the Lorenz equation. But there are some important differences in fully developed turbulent flow and chaotic flow. But chaotic flows occur at the transition regime. In fact, periodic flows also occur at the transition regime from steady state to dynamic in fluid mechanics. Okay? These are some important concepts. Please ask me if there are any questions. Is it clear what I'm talking about? Or you're already in 35,000 square feet high.
With the nonlinear system, if you don't necessarily a priori know the number of steady states, for a chaotic system, can you say for sure that it never closes on it, that it never reaches a limit cycle?
Remember, I tried to clarify what we mean by solution to the dynamical problem versus solution to the steady state problem.
Right.
Solutions to the steady state problem, there could be many and we don't know all of them.
Right.
But the solution to the dynamical system is unique. For a given initial condition, there can be only one trajectory. That is for a given initial condition. But if I have different initial conditions, I could have different trajectories, and each one could go to different steady states. Or they could go to the same steady state. You could have something like this. Right? So I have two initial conditions that goes to the same steady state. That's one possibility.
Right.
The other possibility is I have a different initial condition that goes to a different steady state. Here both of them must be stable. There could be some unstable states that I will never be able to go through this path, but I can find them by solving the steady state equation using Newton method. And there are also possibilities at different initial conditions that I might have cyclical behavior, right? So I'm not really sure whether I understand your question. Can you rephrase it?
Well, I thought before you said that you don't necessarily always know the number. Did I misunderstand that you don't always know the number of steady states?
That's true. You never know a priori the number of steady states for a given problem.
So if we integrate the Lorenz equation longer than anybody's ever integrated it, can we be positive that there's not some curve on there that it won't just stay in a periodic?
If you're going to use numerical ways of getting at it, there is no way that we can assure, because we need to sample the entire state space for different initial conditions. We need to change the initial condition from minus infinity to plus infinity in x and in y and in z. We will never be able to do that. And the funny thing with all these problems, and you will see in the undergraduate course, the parameter, if it changes from 0.7995 to 7997, the behavior will change. It's so sensitive to the parameter values, right? So to span the entire parameter range is going to be a difficult problem. But what we are saying is that in a strange attractor, there could be nearby limit cycles. We are not ruling that out. So if you start from a different initial condition, you could go to a nearby limit cycle, or you can go to a nearby steady state. You could have. So these can coexist. A steady state can coexist with a limit cycle, which can coexist with a chaotic response. But a chaotic attractor will have a certain region of attraction. So if your initial condition lies within that, it is caught in that, and it will have that response. Okay. Any other questions? So the short message, I guess, is it's complex, it's fascinating, and we will never know the full truth. Okay, but for nonlinear systems, we will never know the full truth. So this is taken from the book by Collins. So it's basically a sketch that shows that you can have a steady state, a trajectory attracted to the steady state in state space. You can have a limit cycle, which is the solid line that you see here. And you can have trajectories from either side, inside or outside, attracted to the limit cycle. Now you can ask the question, can I have a limit cycle that's a repeller? If you can have a steady state point that's an attractor and a steady state point that's a repeller, can you have a limit cycle that's an attractor and a limit cycle that's a repeller? It's a very valid question, and the answer is yes. But you will never know using integration methods alone, because a repeller will not, the trajectory will not go to that. So you need to use analytical methods to track whether such things exist or not. And this is the so-called strange attractor, where the trajectory is thought to live on a kind of a torus. Okay, so it has some sort of a period on a short time scale, another one on a longer time scale. Okay, so that creates it to completely fill without ever crossing the trajectory. So if you have a mechanism like this, once it comes back, it just lives on the donut surface, right? And you can draw infinitely long curves that doesn't intersect itself. Did I exceed my time? When I talk about exciting things for me, I don't notice the passage of time. So are we out of time? I guess we are.
Yes.
Okay, so we will continue with it on Monday. Okay, thank you.